this distance? Well, so instead of choosing it from all of RD in this case, if these are points, you could actually choose it from the set. So restrict that the center is one of the points of your set X at your cluster. And if you do that, so it minimizes this cost function among all of these points, then it's, as long as it's, at least as long as it's a metric. If it's not a metric, some weird things may happen. But if it's a metric like the Jaccard distance, this will still decrease this cost. So that means that both of these steps are decreasing the k-means cost, and this will still converge. So you can still run some version of this, and it'll probably work pretty well. But by picking the centers to be elements of the set. This is a bit harder to do. You probably want to check all the different centers. And so this kind of, if you have roughly n over k things in here, you're going to take n over k squared time to do this check. Because you need to, from every point, check the distances to all the other points. Sometimes you can pick a bunch of random points, a random subset, and just check those. Always include the current center, otherwise your cost may increase. So this does not work as generally as the Gonzalez algorithm. The k-means plus plus is just as general, right? All you need is you're picking centers from your set, and all you need to do is calculate this assignment function. So as long as you can calculate this distance, you can't really define this function without a distance, then you can still run that algorithm as well. And that will work pretty well. And maybe some version of this will optimize it a little bit, but that may hopefully give you a pretty good answer without even doing more iterations. Okay, so one more thing is there's this k-median variation. How do you think I would solve that problem? I now want to minimize the sum of the distances, not the squared distances. Right? This actually seems like a much more natural definition of the problem. It's actually going to be more robust to outliers. Remember this example where I had this one outlier point, and I'm trying to choose which of the points to pick as a center. Well, I looked at the squared distance from here. So if this distance was 10, and these distances were 5, well, this is twice as big, but I'm going to pick it 4 times as likely because I'm squaring, right? So this squared becomes 100 and this becomes 25, and this kind of increases the power of these outliers. If I just, use 10 and 5 and that was my cost, that seems much less sensitive to these outlier points. So that one seems much more natural. So why don't people use k-median clustering?
Because it is, for many dimensions, it is difficult to define a median.
Well, no, I've defined what's called the L1 median here. Actually, I want to find the set of centers which minimizes that cost. So it's not, it's kind of like this high-dimensional median problem. So yes, that's basically, that's probably the right answer. So this step I can do the assignment. This works for any of the cost functions. But choosing the centers becomes harder. Okay? The average no longer minimizes the sum of the distances. So it turns out that there's solving the point that minimizes the sum of the distances is a really kind of is a computationally hard problem. It's kind of you're comparing square roots. Remember, the distance was the square root of a sum of squares. And square roots are actually a hard to compute entity, and comparing which is better or even optimizing over them becomes very difficult. So there's actually some kind of iterative algorithms that can try and minimize. So if you just look at this cost function and cross off the 2, then you want to find this argument endpoint here. And you can actually do some gradient descent type algorithms to try and minimize this. And some of those work pretty well. But finding this point is called the Fermat-Weber problem. And it's a well-known hard problem that people don't really know how to solve. And there are various heuristics, but it's harder to do in practice. And so you can't just simply take the average, which is very simple. You can do each of the coordinates independently. So this step is much harder for k-median, and that's why people don't do it. They do it because, usually because they're lazy, and people have written code that does k-means. So why don't we use k-means? And generally, if your data, again, the point is if your data is well clusterable, k-means will probably work really well. If you have some outliers and k-means get stuck, well, maybe there's a few cases where the k-median will do better than k-means. But these are kind of fairly rare. Usually, if you have too many outliers, then your data clustering does not work very well in general. But if you have a few, there's some boundary where k-median will work a little bit better than k-means. But it's kind of actually hard to construct these examples. They can come, there's a very small space where one works really that much better than the other. So it's probably okay to be lazy and use k-means. But if you do get stuck, do random restarts or start with the k-means ++ and do random restarts. Okay. So remember, the homework is due next week, Wednesday, and there's no class on Monday because it's a university holiday.